Okay. Um, okay, let's take roll. Today is the 7th. All right, let's see who is here. Hersey is here. Gilcrease is here. Lackey, not here. Luna is here. Macias is not here. McKinnon is not here. Morris is here. Powers is here. Renfro not here. Salvador not here. Spivey is here. All right. So we're going to start our new chapter dealing with nuclear chemistry. Bring this PowerPoint up. Okay, so here we go. All right, so nuclear chemistry is what we'll be talking about today. And let's remind ourselves of certain terms that, of course, you would have met before. Namely, the mass number of an element, which would be the sum of the number of protons and neutrons, and the atomic number, which would be the number of protons in the nucleus of an atom. These are important because these are the particles, or these deal with the particles that are in the nucleus. And in nuclear chemistry, we're dealing with nuclear reactions where basically the changes will take place in the nucleus of the atom, all right? So there'll be changes that will take place as far as the atomic number is concerned, which will be the number of protons, and the mass number is concerned. In some cases, the atomic number won't change, but the mass number will change, and vice versa. So that's basically what we'll be dealing with in this chapter. So the symbols that are used typically when it comes to representing these numbers would be that the mass number would be represented by the letter A, uppercase, and the atomic number would be represented by the Z. So therefore, we can have what is called an isotopic symbol for a particular nucleus, which would look like this, where A is placed as a superscript on the left, and the Z would be placed as a subscript. And the X, which would represent the element symbol, would be in a regular size in terms of its representation, right? So this is just basically a shorthand way of describing the nucleus of a particular element. There are some other particles that will come into play. You're going to see over and over again in this chapter. Proton, right? We all know what the protons are. They are positively charged species, and the shorthand way of representing a proton would be this or this. We have 1 and 1 here as subscripts and superscript. And basically what this is saying, if we're going by this guide right here, is that the mass number of the proton is 1 and the atomic number is 1, right? Or you can use H instead of P because the actual element is hydrogen. So either one will do. Another particle that you will meet is the neutron, right? Which has a mass number of 1, but you'll notice here that the subscript here is 0, right? And that doesn't mean that, well, basically that would, is basically the atomic number, so to speak, in air quotes, but basically we use 0 for the atomic number for the neutron, right? So A would be equal to 1 and Z would be equal to 0. And then another particle that you'll meet is the electron, also known as a beta particle when it comes to nuclear reactions, right? And you'll notice here that the mass number is 0, right? And this is kind of different from the others. The atomic number is -1, right? And that's because the charge on the electron is, of course, -1, right? So you can use this symbol or this symbol to represent the electron, which is also called the beta particle when it comes to nuclear reaction. And then there's this particle, which is seen to be the opposite of a beta particle. It's called a positron. And the difference between the positron and the beta particle is that down here we have a +1 for the atomic number, which indicates that the charge carried by the positron is +1. So you can use this or this to represent the positron. And then there's one more particle, which is known as the alpha particle, which is the same thing as the helium-4 nucleus. And as you can see here, the mass number of the alpha particle is 4, and the atomic number here is 2, and you can use this symbol, or you can use this symbol here, alpha instead of He, because that's a common name for that particle, the alpha particle. So the mass number of the alpha particle is 4, and the atomic number is 2, all right? So those are basically most of the particles, fundamental particles that you're going to meet, in addition to other nuclei for different elements, all right? So let's talk about how do we balance nuclear equations. So as I said before, the changes that will take place in the nucleus is what occurs in a nuclear reaction. And that is fundamentally different from chemical reactions, right? In the case of chemical reactions, you don't have any change in the nuclei, you have change in the number of electrons around the nucleus, especially the valence electrons. But in the case of the nuclear reactions, there will be changes in the nucleus in terms of the mass number and or the atomic number. So what you'll find is that to a certain extent, balancing a nuclear equation is actually easier compared to balancing a chemical equation. Basically, you have to observe two rules. One of them is that you have to conserve the mass number. In other words, the number of protons and neutrons in the products of a nuclear reaction must be equal to the sum of the number of protons and neutrons in the reactants, right? So here's an example, right? And this is actually a reaction that is used to power nuclear power plants which generate electricity. We used to have one in Citrus County here, but it has been decommissioned a couple of years ago, but we'll get into that later on. This is the reaction where a uranium-235 nucleus is bombarded with neutrons, and you end up with these products, right? Now, this equation is balanced. Why? Because if you take the sum of the mass numbers, right? The 235 plus 1 on the left side, that gives you 236. And then you compare that to the sum of the mass numbers on the right side, 138 plus 96 plus 2 times 1, right? They both give you the same answer, which is 236, all right? So that is how we conserve the mass number, right? And then the atomic number must be conserved as well. In other words, the total sum of the atomic numbers on the left side must be equal to the total sum of the atomic numbers on the right side, right? So in this example, if you add up 92 plus 0, right? And then on the other side, you add 55 plus 37 plus 0, 2 times 0, then you're going to end up with each side be equal to 92. So therefore, the atomic numbers will be conserved as well as the mass numbers. And basically, that's what you look for in terms of balancing nuclear equations, all right? So just to recap, to balance nuclear equations, you have to make sure that you conserve the mass numbers on both sides, all right? And also you conserve the atomic number on both sides. That's basically it, all right? So it's a bit more straightforward compared to balancing ordinary chemical reactions. All right, so I think I have an example lined up here. It says polonium-212 decays by alpha emission. Write the balanced nuclear equation for the decay of 212 polonium, right? So basically, it says that it decays by alpha emission. So that's one key thing you need to be cognizant of. You need to know the symbol of the particles that is stated in the question. In this case, it says it decays by alpha emission. So it basically gives up an alpha particle. So just to remind you, an alpha particle can be represented by either this symbol or this symbol, right? So what we do is start off with the polonium-212, and we have to look up the atomic number. So you consult the periodic table, and you see that the atomic number of polonium is 84. And then you write an arrow, and then on the right side of the equation, you put the symbol for the alpha particle, right? And then now you put this as your unknown, the unknown nucleus, X, with the mass number of A and the atomic number of Z. So keeping in mind that the mass numbers and the atomic numbers must be conserved on both sides, then you can write down an equation, well, two equations actually, one relating the mass numbers of the element or the nucleus on the left to those on the right, and another one relating the atomic number of the nucleus on the left to what is present on the right. So in terms of the mass numbers, we start off with the 212, right? and we set that to be equal to 4, which is the mass number of the alpha particle, plus A, which is unknown for your particular nucleus on the right side, represented by the letter X. And then you solve for A, which is a very simple process. You're going to end up with A of the element or the nucleus on this side being equal to 208. Then we do the same thing with the atomic numbers, right? 84, which is the atomic number of polonium, is equal to 2, which is the atomic number of the alpha particle, plus the atomic number of the element unknown Z, X, which is Z. And then again, we do the simple arithmetic to solve for Z, which is equal to 82, right? So we know that this element here, or this nucleus here, has a mass number of 208 and an atomic number of 82. So now we need to identify X. What is X? And that's very simple. All you have to do is go to the periodic table and look up the element that has the atomic number 82, right? And that's all you do. When you do that, you're going to see that that element is lead, and therefore you replace the X with Pb, the symbol for lead. And that's basically how you end up with your balanced nuclear equation for this reaction, all right? Any questions about this? Any questions? Any questions out there in Zoom? Any questions? Okay, so okay, before we do that, let me go to assignment number 8. And I'm only one person sitting in class here, so I'm just going to give her a copy of that assignment, because the first couple of questions basically is an exercise in balancing nuclear equations, just like we did before. So I just want to go, I'm not going to go through all of them. I'm going to leave the rest of them for you to do, but I just want to get you started. So let me go to the Canvas shell for this course and go to Files and go to Assignments and assignment number 8. Let me publish that now. So you guys out there in Zoom should now be able to access assignment number 8, which is what I'm going to do right now. Okay, so this is assignment number 8, and it says here, okay, so it says here that, hold on 1 minute, let me just check something here. Okay. Circle the missing particle in the following nuclear equation. So basically, wherever you see a space, there are options, 4 options, which would be, one of which would be the correct answer, right? So basically, just do what I described earlier. Let me turn on my pen here. Okay, so again, as I said before, what you do is make sure that the mass numbers and the atomic numbers are conserved. So let's start off with the first one. So we have, let's deal with the mass numbers first. We have 214 for the polonium. Now we have a 2 here. That 2 would multiply the 4 here, right? And then we have 0 here, right? And therefore, whatever we get on this side, the mass number should be the same as this side, right? So 214 plus 2 times 4, 8, plus 0 would be equal to the mass number on the other side. So this works out to be 222. So you're going to put 222 would be the mass number for the nucleus that would be placed on the right side. And then for the atomic numbers, we have 84 plus 2 times 2, 4, minus 2, because we have 2 times minus 1 here, right? And that would be equal to whatever the atomic number is. So that's 84 plus 2 equals to 86. So 86 will go here. And then we consult the periodic table to see what element corresponds to 86. I can see it from here. Anybody has a periodic table? Let me come here and download the periodic table. I was trying to look at the one here in the classroom. So let me do the tables. Tables. Okay, so what we do now is look for the element that has atomic number 86. And according to this periodic table here, that element would be, where's 86? 86 is radon, all right? So basically, let me go back to, move this out of the way. So basically, radon would be the answer here, which would be D, all right? And that's how you do that. Okay, any questions about this example, or any question about this first question here? Any questions? All right, I take it it's okay for me to clear this, so let me do that now. And let's scroll down to question number 2. Okay, so let me hear what you have to say about number 2. What would be the mass number for the particle over here? 0. And what would be the atomic number for the particle over here? -1. So what does that correspond to? C, exactly. So the beta particle is the only particle that has -1 for the atomic number and 0 for the mass number. Okay, let's do one more and then we'll move on. Let me clear this here. And scroll down. Okay, for number 3, identify the missing particle again. So let me hear what you have to say about this one. Get my calculator. What's the total mass number on the right side? I'm going to put A here. What is A equal to on the right side? The total mass number on the right side, I should say. The sum of these. And remember, multiply by 3 here.
135.
Oh, I got something different. Let me try again. Plus 3. I got 236, actually. Folks,
This one's supposed to be minus.
What's that?
Oh, I thought it was gonna be -1 because the thing on the left. Oh, sorry, I got a bit ahead.
No, I was asking for the total, right? Hold on, somebody said something online here. Okay, yes, Miss Macias, you're correct, 236. Okay, so that's a total on the, whoops, I'm sorry, on the right side. And what's the total atomic number on the right side? Yeah, that's what I got to, 92, all right? So with that said, 92. Okay, so with that said, the total on this side must be the same. So for the element or the nucleus here, what would you think the atomic number is? I'm sorry, not the atomic number, the mass number. What do you think the mass number is? Now remember, you have that 1 there for the neutron on the left side. So what would be the mass number for the nucleus right here? Okay, somebody online said, what? Let me see here. 235 is indeed correct, and that's Mr. Powers who said that. All right, so 235 would be on this side. And what would be the atomic number for that nucleus on this side here? Yeah, I need to keep checking the chat. "92 is indeed correct, and that was Miss Macias and Mr. Powers who answered. Okay, so what element, remember now, to identify the actual element, we have to go to the periodic table and look up the atomic number of, the element that has the atomic number 92. So that would be what? What element would have the atomic number 92?
Oh, periodic table on me.
Uranium is indeed correct, Mr. Powers. So that would be the answer. That means that the answer here would be A, all right? Okay, so based on what we have just done, you should be able to do up to and including, let me scroll down here. You should be able to do all questions up to, hold on, let me clear this first. You guys should be able to do all questions up to and including number 20, right? So there are 20 such equations that you need to identify the missing particle in each case, right? And it's the same process. Total mass number on one side must be equal to the total mass number on the other side. Total atomic number on one side must be equal to the total atomic number on the other side. And then basically for the unknown particles, to identify that, you solve for the atomic number of that particular particle, and then you look up the element that matches it in the periodic table, and that's pretty much it, right? That's how you determine the missing element, or missing nucleus, or missing particle.
Professor,
Yes, ma'am.
I had a question for number one.
One. Okay, let me scroll back up here.
In the options, we don't get, like we already get some numbers, but why do we only add 84 plus 2 and we don't subtract the 1?
I thought we did. 84. Let me check again. I'm sure I did. 84. Oh, hold on. It's 84 plus 4. Because, let me turn this on here.
Oh, yeah, you're right.
You know what I'm saying? You have 84 here. You're talking about the atomic numbers, right?
Yes, because we ended up having, getting 86 at the end.
84 plus 4, that's 88. And then minus 2.
Oh, okay, now I see.
You know what I'm saying? 84
Yeah, that
plus
makes sense.
times 4, 2 times 2, 4. So that's 88. Minus 2. 2 times minus 1, minus 2. So that gives you 86.
Okay, got it. All right, thank you.
Right? Okay, and you know, I'm glad you asked that question because it gives me the opportunity to warn you that you have to be careful, right? A very common error that students tend to make is some little minor things, like for example, to multiply this here by 2, for example, or multiply this here by 2, right? Little things like that can affect your answer negatively, pretty much, all right? So just take your time when you're solving these problems, just take your time and try to account for everything that the equation gives you, all right? Okay, any other questions before we move on to the next topic? Any other questions? Okay, okay, so let me clear this. Let me do this and let me scroll down. Oh, actually, let me go to the PowerPoint. Okay, so let's talk about the differences between chemical reactions and nuclear reactions. And there are a couple of differences. The first one, in a chemical reaction, and this is something that we know already from before, what you have happening in a chemical reaction is that atoms are rearranged, you have bond breaking, you have bond making, and that results in the formation of new products, right? But there are no changes in the nucleus of the atoms involved. Basically, the changes would be in the number of electrons in the valence shell of these atoms, all right? In the case of nuclear reactions, you have elements or isotopes of the same elements are converted from one to the other. So basically in nuclear reactions, you actually have the conversion in most cases, if not all, well, in most cases, you have the conversion of elements, one form of element or one element into another, or if it's the same element, one isotope to another, all right? So that's one, and the first difference between chemical reactions and nuclear reactions. The second difference I just mentioned earlier actually is that only the electrons in the atomic or molecular orbitals are involved in the breaking and forming of bonds. But in the case of nuclear reactions, you have the protons, the neutrons, and electrons, and other elementary particles may be involved, all right? The third one is a very important difference. And this has implications, especially when it comes to meeting energy needs of our current society. Reactions, in the case of chemical reactions, these reactions are accompanied by the absorption or evolution of a relatively small amount of energy, all right? When you compare that to nuclear reactions, the amount of energy absorbed or released is huge compared to the amount of substances involved, all right? And we're going to talk about that in a bit more detail later on, all right? And then the fourth and final difference between a chemical reaction and a nuclear reaction is that the rate of a chemical reaction, as we learned earlier, I think the second chapter that we started off in this course, we learned that the rate of a reaction the rate of a chemical reaction is affected by several factors: temperature, pressure, concentration, and catalyst, right? So if you remember when we were talking about rates of reaction, you know, for example, generally speaking, increasing the temperature will increase the rate of reaction. Generally speaking, increasing the concentration will do the same. Catalyst would, of course, affect the rate of reaction and so on. But when you compare that to nuclear reaction, that's not the case, right? It doesn't matter what you do to the temperature. There's no such thing, as far as I know, as a catalyst for a nuclear reaction. Pretty much nothing else or nothing will affect the rate of a nuclear reaction compared to a chemical reaction, all right? So basically, those are the four differences between nuclear and chemical reactions. Okay, what's next? All right, so let's talk about the different types of decay and the effect that it will have on the nucleus in terms of the stability of the nucleus. So beta decay, beta, of course, the beta particle is basically an electron. We just use the term beta when it is either used up or produced in a nuclear reaction, right? So this is what happens when carbon-14 undergoes beta decay to form nitrogen-14, and this symbol here represents radiation, electromagnetic radiation that's being produced, right? So that's what happens in each case, right? Here's another example. Potassium-40 will also undergo beta decay to form calcium-40, and also radiation would be formed, right? Now, in each of these cases, and this is true for all beta decay, there'll be a decrease in the number of neutrons by 1, right? So if you look at the first reaction here, right, you see that the atomic number increases from 6 to 7, but the mass number remains the same, which means that there'll be a corresponding decrease of neutrons by 1. And the reason why that happens is that each time a beta particle is produced, it is produced by this reaction here, where a neutron will undergo a reaction to form a proton and the beta particle. The beta particle and the radiation will leave the nucleus that is formed, and the proton will remain in the nucleus, right? So that's why the atomic number in each of these cases increases by 1 because a proton is formed, and the mass number decreases by 1 because a neutron is used to form the proton, all right? So that's what happens in the case of beta decay, all right? So decrease of the number of neutrons by 1, and the number of protons will increase by 1 in every time a beta decay occurs. In the case of a positron decay, such as in this example and in this example, right? Again, radiation will be formed as a result, all right? Or produced as a result. And you'll notice that in the case of positron decay, the atomic number in each case would decrease by 1. So in this case, the atomic number of carbon-11 decreases from 6 to 5 in the case of boron-11. In the case of potassium-38, the atomic number decreases from 19 to 18. And why does that happen? Well, obviously that means that there is a decrease in the number of protons and a corresponding increase in the number of neutrons. And the reason why that happens is because in the case of a positron decay, the proton here will be converted to a neutron plus a positron, right? So basically, the number of protons will be decreased by 1 because the proton is converted to a neutron. And because a neutron is produced in this reaction, the number of neutrons will increase by 1 in each case where you have a positron decay, all right? Okay, so that's what happens in the case of a positron decay. All right. Oh, and one important point being made here, these symbols, as I said before, represents radiation. Radiation basically, for the purposes of nuclear reactions, basically will have no mass numbers or atomic numbers. So therefore, we don't take them into account when we're looking at balancing these equations, right? Okay, so that's what happens in the case of beta decay and positron decay. Then we have what is called electron capture decay. And as the term suggests, basically what is happening is that a nucleus of a particular element is capturing a beta particle or an electron, and therefore a new product, a new nuclei or nucleus will be produced. So what happens in this case here is that, as you can see in this example, and in this example, the atomic number decreases as you go from the original nucleus to the product, right? So the mass number remains the same. Same is true for the second equation here. So what actually happens in this reaction is that a proton will combine with an electron to form a neutron. So for that reason, the proton, since it's reacting, would result in a decrease in the atomic number from 18 to 17 here and from 26 to 25. And the mass number will remain the same because the proton is converted to the neutron. The mass number doesn't change, so therefore chlorine 37 will have the same mass number as argon 37, and manganese 55 will have the same mass number as iron 55. So that's what happens. There's an increase in the number of neutrons when this happens, but the number of protons will decrease as well. All right, but the mass numbers will not change. All right, and then we have alpha decay. Now remember, the alpha particle is a helium-4 nucleus, right? And this is actually the first example that we worked in this particular chapter, where polonium-212 will undergo an alpha decay to form lead-208, right? In every case of an alpha decay, what happens is that the number of neutrons will decrease by 2, and the number of protons will also decrease by 2, which means that the mass number will decrease by 4, all right? So that's what happens in the case of every example of an alpha decay. You can have certain situations where we have what is known as spontaneous fission, where one huge nuclei or nucleus will simply split up spontaneously to form smaller particles, such as you see here. In the case of californium-252, that would split up to form these particles here, 2 particles of indium-125, along with 2 neutrons, all right? So we're gonna see some examples of that later on, all right? Now, this begs the question, how can we predict whether or not a particular nucleus will undergo any sort of spontaneous fission, right? And it turns out that, and this was looked at, people did research and tried to figure out, okay, what makes a particular nucleus stable, right? And they did an examination of different types of nuclei, and they found that at lower number of protons and number of neutrons. Let me explain what's happening here. We have the number of neutrons plotted versus the number of protons in order to see if the neutrons per proton ratio has any effect on the stability of the nucleus, right? And it turns out that at lower atomic numbers, right, it seems as if the number of neutrons and protons would be equal or roughly equal or nearly equal, all right? But as you get to heavier elements, heavier nuclei, what you'll find is that that ratio for stabilities of the nuclei tilt towards the neutrons. In other words, the ratio of neutrons to protons would be greater than 1 as you go higher and higher in terms of the heavier nuclei, all right? So basically, this is called a belt of stability in this particular plot, right? Basically, elements or nuclei which falls outside of that belt of stability will undergo nuclear reactions to produce products which will fall closer to the belt of stability, all right? So that's basically what was observed experimentally when they looked at the stability of different nuclei, all right? So basically, if the ratio of neutrons to protons is too large, then we tend to have, those nuclei tend to basically emit beta particles, right? So that the resulting product would fall closer to the belt of stability. If the ratio is too small, then they tend to undergo positron emission or electron capture to form a nuclei that would be closer to the belt of stability, all right? So That's basically what has been observed in terms of trying to understand and make predictions about the stability of nuclei based on the neutron to proton ratio. Okay, okay, so that's that. So some other ideas, this is just basically general trends that have been observed for determining whether or not a particular nucleus is stable. It turns out that certain numbers of neutrons and protons are extra stable when they're present in a nucleus. So it turns out that if the number of protons or neutrons is equal to these numbers here, they tend to be stable, right? And extra stable numbers of electrons in noble gases, of course, it's kind of comparable to that. Just as how we know that, elements that contain these numbers of electrons are stable, then it seems as if when it comes to the number of protons and neutrons, these numbers would confer some stability to the nucleus. And to be perfectly honest, I don't think the reason for the stability has been fully understood yet, at least as for the last time I checked. Things may have changed since then, right? Another thing that is observed is that nuclei with even numbers of both protons and neutrons tend to be more stable than those with odd numbers of neutrons and protons, right? That's another observation that has been made when people try to figure out what makes a nucleus stable, all right? And one thing that is observed as well, another additional fact here, is that all isotopes with atomic numbers higher than 83 are radioactive. So that's probably the easiest one to predict. So basically, if you have an element whose atomic number is 83 or above, you can assume that they are radioactive. That means that they will spontaneously undergo a nuclear change to form other nuclei. All right? And the table that you see below here is basically a summary of some other ideas, some of which were mentioned before, concerning making predictions of the stability of nuclei. So if the number of protons are odd and the number of neutrons are odd, it turns out that the number of stable isotopes will be equal to 4. If the number of protons are odd and the number of neutrons are even, the number of stable isotopes goes up to 50. If the even and odd numbers switch for the protons and neutrons here, that goes up to 53. And it turns out that if both the number of protons and neutrons are even, the total number of stable isotopes will be 164. All right? So that's basically all we can say concerning making predictions of the nuclear stabilities of isotopes. All right? Oh, by the way, there's another thing that just showed up here. All isotopes of technetium and PM. I don't remember what PM stands for. All isotopes of those two elements are radioactive. Okay, so that's as far as nuclear stability is concerned and making predictions of nuclear stability. Okay, now quantitatively speaking, one of the ways that we can tell whether or not a nucleus is stable is by first looking at what is called the nuclear binding energy. And as stated here, this is the energy required to break the upper nucleus into its components, protons and electrons and neutrons, right? So basically, if you have, let's say, fluorine-19, let's say you have that nucleus, right? Based on the symbol here, we know that fluorine-19 has 9 protons and 10 neutrons, right? So what the nuclear binding energy is, it is the energy required to break up this nucleus into the separate particles that are present in the nucleus. Now, let me just say this before I move on. And I think I remember making this point for those of you who was enrolled in my Chem 1 class previously. I remember saying that it turns out that the total sum of the masses of the protons and neutrons present in an atom is not equal to necessarily the masses of the atom itself, right? If you add up the protons, neutrons, and electrons in an atom in terms of the mass of each of those particles, that will not be equal to the mass of the atom. That may seem to be counterintuitive, but there's a reason why that happened, and it has to do with the nuclear binding energy. Okay, so let me explain how we calculate that nuclear binding energy. The formula for calculating the nuclear binding energy is this right here. The energy is equal to delta M times C squared. Now let me explain what each of these terms mean. Delta M is called the mass defect. Delta M is equal to the mass defect. All right? And what's the mass defect? The mass defect is the sum of the masses of the different particles that are formed when the nucleus is broken up completely, right? So basically, this is the way we calculate the mass defect, right? And that, unfortunately, that's not shown here. That would be equal to, in this case, 9 times the mass of the protons plus 10 times the mass of the neutrons. And these numbers would have to be given to you in order for you to calculate the delta M. Another thing that you need to do is add those numbers up, right? And you subtract from that the total mass of the nucleus, which is broken up to form those particles, right? So these are the masses. This is the mass of the proton in AMU units. This will be the mass of the neutron in AMU units. And this will be the mass of the fluorine 19 nucleus, again in AMU units, right? So basically you add the total mass of the protons and the neutrons present, add them up and subtract from that the mass of the nucleus of the fluorine. And when you work that out, according to what I have here, that gives you 0.1587 AMU, right? Now, there are a couple of ways there are a couple of approaches you can take. The approach that is shown here in this PowerPoint is that 1 AMU is equal to 1.49 times 10 to the minus 10 joules, right? So basically, all you have to do is convert 0.1587 to joules using this here. So in other words, 0.1587 AMU multiplied by 1 AMU down here and 1.49 times 10 to the minus 10 joules above. And when you work that out, that gives you this value right here. So that represents the binding energy of the nucleus, right? Now, another way of doing it is by using this equation I showed you earlier, right? Basically, what you'll do is put this number here. In fact, let me show you down here, all right? So what I would do if I were to use this equation here is say E is equal to the mass, which is 0.1587 AMU. And then you'd have to convert that to kilograms. And I don't remember what the conversion factor is. Let me get out of this here. Sorry. Let me go to the tables. Okay, 1 AMU is equal, okay, 1.66 times 10 to the minus 27 kilograms, so okay, so here I'll put 1 AMU is equal to 1.66 times 10 to the minus 27 kilograms. And then I'll multiply that by C. C is the speed of light, which is always 3.00 times 10 to the 8 meters per second. And then I'll square this, right? And then when you do that calculation, that will give you the same answer, which would be this right here, 2.37 times 10 to the minus 11. So those are two ways you can go about calculating the binding energy, all right? Personally speaking, I prefer it this way because this shows you how the units cancel out. But you can still use this way or this way. You can use this way to determine that value as well as this method right here. So either will do as far as I'm concerned. You'll get the same amount of credit regardless of which method you choose, all right? So that's basically how you determine the binding energy, the nuclear binding energy for any nuclei, right? So of course, you'd have to be given these values, the 1.007825 for the protons and the 1.00865 AMU for the electrons, all right? And that's basically how that is done. I'm sorry, for the neutrons. Okay. Now, another thing I need to mention, and this is the actual measure of nuclear stability. Well, let me ask you first, can I clear all this here? All right, so let me clear this here. Okay, where is this? Oh, wrong thing I'm looking at. Okay, I guess I messed up here. Okay, let me just try to explain what's happening here. For some reason, I can't clear all that, but what I want to point your attention to is down here, right? This is the actual way we determine the stability of a nuclei or nucleus quantitatively. We calculate what is called the binding energy per nucleon. Now, the term nucleon you may not have met before. Nucleon basically are particles present in a nucleus, right? And of course, those are the protons and the neutrons, right? Those are the particles that are present in the nucleus. So collectively, they're known as the nucleons, right? So the binding energy per nucleon is the binding energy that we calculated earlier, divided by the total number of nucleons, which in the case of the fluorine nucleus that we're dealing with, that would be equal to 19. So we take the value that we calculated here, which is 2.37 times 10 to the minus 11, divided by 19, and that gives you the binding energy per nucleon. And something is missing from this here. Let me add it here. This should be joules per nucleon. All right, so please make a note of that, right? So that's basically how you determine, or I should say more accurately, how you measure the stability of the nucleus, all right? So based on that type of calculation for different types of nuclei, we end up with this plot right here, right? We plot the mass number, right, versus the binding energy per nucleon, right? And this is what we get. This plot is what we obtain right here, all right? And from the look of things, the most stable nucleus that exists is the iron 56 nucleus, right? Because it occupies the highest value here, which is about 1.5 times 10 to the minus 12 joules per nucleon, all right? So that's basically how we determine the binding energy per nucleon, which is a reflection of the stability of the nucleus, right? So basically, the greater this value that is calculated, the greater would be the stability of the nucleus, all right? And I want to show you this here. This is called, this is called a decay series. Different radioactive elements will have different series where basically you have the radioactive element undergoing a certain type of decay to form, different product. And then that product, being radioactive itself, will undergo decay and it just continues. And this is the result when you start off with uranium-238. Basically, it forms an alpha particle and another product here, which is thorium-235. 234, I'm sorry. And that also undergoes decay, this time a beta decay, to form this particular nucleus, whose name I can't recall right now, and so on and so forth, right? So basically, uranium-238 will undergo a series of decays to form different products. And there are some numbers that you see here, which represent half-lives. We're going to talk about the kinetics of radioactive decay later on, all right? But I just want to point out, and this has some implications in terms of how we discard radioactive waste, especially, the waste generated from power plants and so on. Because you'll notice, for example, uranium-238 here, its decay has a half-life of 4.5 billion years, right? That's a very, very long time, as you can imagine. And one of the concerns that people have is, how do we deal with these wastes? Because the waste itself is radioactive and can, if the radioactive waste gets into groundwater or in the atmosphere, can cause, of course, some serious health damages. So therefore, the question now becomes, how do we deal with these wastes when they're generated? So we're going to talk about that later on, all right? But I just want to show you this as an example of a decay series, and that's for uranium-238, and other radioactive elements have other decay series as well. Okay, so let's talk about the kinetics of radioactive decay. And the first thing I'm going to say here is, and again, this is another difference between radioactive, or I should say nuclear reactions, or in this case, nuclear decay and chemical reactions, is that when it comes to radioactive decay, their decay is always a first order process, all right? So there's no such thing as a second order or zero order decay process when it comes to radioactive decay. All right, so basically what happens in a nuclear reaction is that you start off with your original nucleus, and then it basically undergo decay to form what is called a daughter nucleus, right? Which is produced directly from the original nucleus. So we can write down an equation expressing the rate of the decay, which is equal to minus the change in the number of nuclei divided by the corresponding change in time, all right? Now, we can actually measure what is called the rate based on what is called the activity, right? And the activity is something that you can measure using an instrument known as a Geiger counter. I'm going to show you how that works in the next slide. But basically, from the Geiger counter, you can measure directly the activity. And the activity is equal to lambda times n. Now, n is the number of nuclei, and lambda is called the decay constant. Let me see if I have it here. Okay, so here it is. Lambda is the decay constant, right? So basically, we have two equations here. Rate is equal to this, and rate is equal to activity, which is equal to lambda n. So we can set this to be equal to lambda n, and this is the equation we're going to end up with. And when we do integration and so on, some calculus is involved, you're going to end up with n, which is the number of nuclei present at time t, is equal to the initial number of nuclei times e to the minus lambda t, right? And another way of expressing it is lambda n is equal to lambda n 0, the initial n value, minus lambda t, right? So we can use this equation or this equation depending on what the question is asking for, all right? And as I said before, lambda is a decay constant. And we can also calculate the half-life. Now, in the case of chemical reactions, we say that the half-life, T half, is equal to ln2 over K. In the case of nuclear reactions, the half-life is equal to ln2 over lambda. So lambda is kind of like the rate constant, but in this case, we call it the decay constant, right? So basically, these are the equations which govern the kinetics of radioactive decay, all right? Okay, so as I said before, and as stated down here, we can measure directly the activity of a radioactive substance using a Geiger counter, which is, I'm going to show you in the next slide. But I just want to show you here the plots of n, which is the number of nucleus on the x-axis versus t, and you're going to get this curve, which should look somewhat familiar to you because this is the same thing that we would observe for a first-order reaction, a first-order chemical reaction. And then if you plot ln n versus t, you're going to get a straight line graph with a negative slope, and that slope would be equal to minus lambda, right? And the intercept on the y-axis would be equal to ln, the initial number of nuclei, all right? And another thing I should mention here is that since we can measure the activity directly, in these equations, we can replace n and n0 with activity. So A, the activity at time t would be equal to the initial activity times e to the minus lambda t. And here, ln A is equal to ln A0 minus lambda t, right? So, and we can write these two expressions because A is equal to lambda n, right? In other words, A is directly proportional to the number of nuclei. So therefore, we can replace n with A in each of these equations. And that's important too, because I think we're going to see one or two problems where we can do that, all right? Okay, any questions so far? Any questions? Any questions? Any questions out there in Zoom? Okay, so this is, as promised, the Geiger counter, at least a diagram showing you how it works. So basically, let me describe what's happening here. Let me start with this cylindrical object right here. Basically, you have a cylindrical metallic object. I forgot what the metal is, actually. And then you have another pole, which is also metallic right here. This is the anode, and this is the cathode, which is connected to a high voltage source, right? And then we have argon gas that is present here. and we have a window right here, which allows the radiation to enter, right? Connected to the circuit externally is a counter and amplifier. So basically what happens is that each electronic pulse that is detected by the counter right here, it will count it and then amplify it proportionally so that you can get a reading right here, all right? So this is what happens. Let's say you point this cylindrical object here, I would call it a cylindrical probe, I'm sorry. Let's say you point it to your radioactive material. What happens is that the radiation enter the window here, and what it does is that it ionizes the argon gas. I forgot to mention that argon is present in the cylinder right here. So what happens is that the argon gas will absorb some of the energy, which will knock the electron, at least one electron from the argon atom to form the argon ion, right? Plus electron. And then what happens is that the argon ion will be attracted to the cathode, which is the cylindrical object right here, and the electron will be attracted to the anode, right? So basically, each time that happens, a pulse is recorded here, right? And that's basically how it works. So basically, when you point the probe to your radioactive material, right, you're going to have, of course, a lot of particles being ionized, a lot of argon atoms being ionized, and therefore that would be measured here, and that would be registered as the activity of the nuclear material that is basically emitting the radiation. So therefore, that's basically how you determine the activity of the particular radioactive material, and then you can use that to do whatever type of calculation that is required. For example, radiocarbon dating, we're going to see some examples of that as well, all right? So that's basically how the Geiger counter works, all right? So as I said before, that can be used in the form of dating certain artifacts. So let's talk about radiocarbon dating first and the principles underlying that. So basically, there are two reactions that involve this particular isotope, carbon-14, right? That occurs over and over again, where you have nitrogen-14 being bombarded by neutrons to form carbon-14 and a proton, all right? At the same time, you have carbon-14 decaying spontaneously to form nitrogen-14 and a positron, okay? So you have this back and forth taking place where carbon is produced and then used up, right? So what happens is that the carbon-14 level on Earth remains constant as a result of these two simultaneous reactions. And that is also true in the case of living organisms, right? Because basically what will happen is that the carbon-14 will be incorporated into atmospheric carbon dioxide, and living organisms will basically inhale carbon dioxide, especially plants, of course, by process of photosynthesis. And animals will consume plants, so therefore a certain level of carbon-14 will be present in organisms, and that carbon-14 will undergo this reaction here, right? And that reaction produces 14 nitrogen, which will react with neutrons to form carbon-14. So the point I'm making is that in all living organisms, the carbon-14 levels will remain constant. Now, when an organism dies, it will not absorb any more carbon dioxide. So what's going to happen is that the level of carbon-14 that is present in the body or in the plant of living organisms, when they die, the amount of carbon-14 will decrease as a result of beta decay. And therefore, based on the level of carbon-14 that is present at a particular time after death, we can determine the age of the dead organism, like a piece of wood or bones or whatever, all right? Now, there's a limitation to the use of carbon-14 for determining the age of such artifacts, and that is that it works only for objects that are more than 50,000 years old, all right? In order for you to date other organisms with that has less years on it, you'd have to use some other isotopes, all right? Another important thing I need to mention, I have it here, is that in order for us to determine the age, we need a half-life. Okay, here it is. So the half-life of carbon-14 is what you're going to need to determine the age of, such artifacts. And in the case of carbon-14, the half-life is 5,730 years, all right? Okay, so, let me, now, unfortunately, I don't have an example here in the PowerPoint, but this morning I searched online and let me see if I can bring it up. excuse me. I think I've posted it in Canvas and I forgot to bring copies here. Let me see here. Where did I post it? Where did I post it? Oh, here it is. Okay. Okay. So these are just some examples that I've just searched around and I found them. Okay, so let's look at the first question. By the way, do you have a? Okay, yes, okay. Not sure if we'll be able to go through all of these, but let me start off with the first one. So the first question says, what is the half-life of potassium-40 that has a decay constant of 5.3 times 10 to the 10 or minus 10 years? No, I don't remember showing you this, but this is again going from what we learned in chemical kinetics. The half-life, if you remember from chemical kinetics for first order reaction, the half-life is equal to ln2 over k, right? In the case of a nuclear reaction, so this is for first order chemical reaction, right? For a, okay, hold on, somebody says something here. Oh, Ms. Macias, to answer your question, it is located under files. It's right here. I don't know if you can see. Let's scroll down here. Where it says nuclear chemistry examples. All right, okay, good. Okay, so let me go back to the example here. So in the case of a nuclear reaction, the half-life would be equal to ln2 over lambda. Remember, lambda is a decay constant. So this is for nuclear decay. Nuclear decay, all right? So to answer this question, what is the half-life of potassium-40 that has a decay constant of 5.3 times 10 to the minus 10 years to the minus 1? Then the half-life would be equal to ln2 divided by 5.3 times 10 to the minus 10 years to the minus 1. So let's see what that gives. Okay, so according to my calculations, I have to run this off to 2 sig figs. So according to my calculation, the answer is 1.3 times 10 to the 9 years. All right, so that would be the half-life of potassium-40 based on the decay constant given. So that's a relatively simple example. Okay, any questions about this? Any questions? Any questions out there in Zoom? All right, let me clear this. Since I'm using Word, I have to lasso this. Sake of clearing. First question. Let me scroll down. Okay, so this question says, oh no, wait a minute. Let's just go through this one quickly. You should be able to solve this one. Basically, it says complete the nuclear equations for transmutation reaction. Now you'll notice that in this question, they did not give the atomic numbers, so you have to look them up in the periodic table. If I'm not mistaken, neon has an atomic number of 20. And the alpha particle atomic number is 2, I'm sorry, not 4, 2. And oxygen has an atomic number of 8, right? So what would be the atomic number of the element represented by the question sign here? Remember, the atomic numbers have to be conserved, right? You have a total of 22 here for the atomic number, and you have 8 here. So what would be the atomic number of this element? I'm sorry? 14, exactly. And what would be the mass number? Because here you have a total of 24, 20 plus 4, and here you have a total, well, you have 16 here. So what would be the mass number of the element here? Hold on, wait a minute. 16 is. That seems something is wrong here. Hold on. 24. Okay, that seems impossible. 24. There's probably a typo with this particular. 24 minus 16, 8. Okay, I'll hold off on this one here because, I mean, I'm not saying that's not possible, but it's highly unlikely. So let's ignore that one for the time being. What about the second one? Neon has an atomic number. Oh, I made a mistake. My bad, my bad. This should be 10. I just realized that my mistake. I apologize for that. That should be 10. Okay, so let me erase this here. Okay, so what would be the atomic number for the element represented by the question mark? 4?
Yeah.
Okay, and what would be, well, the atomic number would be 8, right? I mean, the mass number, not the atomic number. The mass number would be 8, right? So what element has the atomic number 4? Somebody says beryllium, which I think is the correct answer. In fact, I'm sure it's the correct answer. So Be would be the symbol there. All right. Okay. For the next one, again, neon is 10, and there are 2 of them. So, and oxygen is again 8. So what would be the mass number for the element represented by the question mark? The total here is 20. And here we have 8. So what would be the atomic number for the element here? 12. I would agree with you, Mr. Powers. And what would be the mass number? Because here we have a total of 40, and here we have 16, so the mass number would be what? 24. So what element has the atomic number 12? Magnesium is indeed correct. Okay, last one in this series. Aluminum is 13, hydrogen is 1, and aluminum here is 13 again, right? So what would be the atomic number for the element represented by, or the nucleus or particle represented by the question sign? What would be the mass number? Because here the total mass number on the left side is 29. So, and this is 28 here. So the mass number for this particle is what? 1. And what about the atomic numbers? You have 13 plus 1. So this is 14 right here. And here we have 13. So what would be the atomic number for that particle? That would be 1 as well. So what would be the symbol that you'd use for that particle? H, or we can use 1,1p, proton, all right? Okay, we're gonna stop here for today, and then when we get back next class, we're gonna continue with the C part. Now, you may want to try C on your own, but, try it on your own, and then we'll discuss it next class, all right? Before you guys leave, let me just say that, I've noticed when grading assignment. And I was planning on putting an announcement out, but I forgot, to be perfectly honest. But since I have you guys here, for assignment 5, a good number of you, in fact, maybe only one person, did not do the addendum. If you remember, there are 2 parts. Let me show you in Canvas here. Assignment 5. Okay, so you'll notice that there is one link to assignment 5 here, and just above it is the addendum. As I recall, only one person, I don't remember who that person is, but only one person did the addendum along with the assignment number 5. And I remember at least one person attached another, it wasn't an assignment, it was just an example that I did in class. But they attached that example, which I'm not grading for, I'm not giving credit for that one. I'm giving credit for assignment 5 and the addendum, right? So if you're such a student who have done that, what I would suggest you do immediately is email me the complete assignment number 5 and the addendum together, all right? Email it to me as a PDF document as usual, so that I can grade it and get it back to you, all right? So that's pretty much it for today, unless there are any questions in the remaining 2 minutes. Any questions?
Oh, yeah, question first.
I'm sorry? Oh, somebody online. We turn in the nuclear. Yes, we will turn it in, but we're not finished with it yet because we have to look at some other questions in that chapter. So some of that will be done next week, next class, all right? Okay, what's your question?
Our next exam, it's on the 23rd.
23rd of this month, yeah.
It's gonna be on assignment 5, 6.
I haven't decided yet, but definitely assignment 5, 6, and 7. Not so sure about assignment 8 yet. Maybe, maybe not, but for now, you can start reviewing assignments 5, 6, and 7. All right? Okay, that's pretty much it, folks. So I'm going to sign off. For those of you out there in Zoom, I'll see you next class.
Professor,
Oh, yes, ma'am.
could you take attendance if you didn't take attendance for those who came in late?
Let me see. So Miss Macias. Okay, I've got you, Miss Macias.
Okay.
All right. Okay, so that's it, folks. I'll see you guys on Wednesday.